that work?
Yeah, that's. Okay. Good. So, what's your name, by the way?
Ewan.
Ewan. Okay, I remember. Ewan's going to talk about. Reduction of magnetic order in the hard direction of a Kondo lattice and discrete populations.
Thank you for your introduction, and thank you to the organizers for letting me talk about my research today. I'm Ewan. I'm a first year. You want a mic? I don't know. Can you hear me?
Probably good for the online.
Okay.
Yeah, we say you're a hybrid.
Just attach it somewhere, but not too painful.
Yeah. I'm Ewan. I'm a first year PhD student working at UCL with Michael Quasi-Groch on Kondo systems, particularly looking at lattice ordering in Kondo systems. So these are some experimental results showing susceptibility buttons in many Kondo magnets. The main thing to notice here is that the susceptibility button is always around TK and before TC. So where the Kondo screening is strong and before the onset of magnetic order. And although a lot of these materials have varying degrees of anisotropy, the effect seems to not really depend too much on how strong the anisotropy is, just that there is anisotropy. And yes, the scale for the crossing is always less than TC and around, less than TK and around TC. Therefore, our aim would be to determine a minimal model, the simplest possible model that describes this system without considering particular compounds or microscopic details. So in that regard, we consider an unscreened Kondo lattice so that we can have strong correlations in Kondo, strong Kondo screening, and still have magnetic order. Yes, and it's difficult because, well, it's a difficult thing to do. So our model here is the simplest possible model we can come up with. You just have your usual SRS Kondo exchange with big S is the impurity, spin on less conduction electrons. You have a single conduction electron channel. That's to ensure that the system is underscreened. And then you have a single ion anisotropic term, which is has tetragonal symmetry. This is relevant to many compounds with multiple, or I guess two in this particular case, so F-shell electrons with strong Hundscott. And then you can fermionize the conduction electrons using this expression where the CIs are spinors. So some more motivation for this work. Some previous work that's been done in the group by another PhD from Ponji has showed that the anisotropy in the model is replaced by an anisotropic exchange. This splits equals to 0 at lower energy levels, and you can see that this effect happens in the strong coupling regime where you have large renormalized J's. So perturbation theory does not work. I should stress that this is the single impurity, not lattice as well. So there's no magnetic order. So in that regard, we want to go beyond perturbation theory, because we have large J's, and we want to take into account the entire Kondo lattice, so we can study the effect of magnetic order in the system. So to start, each of the spin 1 impurities consists of 2 electrons, 2 spin half F-shell electrons, which one is dropping. So we take the spin 1 impurity and fractionalize it into 2 spin halves the strong loose coupling to ensure that you project out the S equals 0 state, the singlet state, and then you can fractionalise the impurity in a similar way as the conduction electrons. And then we apply mean field theory to this, so you can rewrite the SRS term in terms of this plus a shift in the chemical potential for the conduction electrons, which is solved as a one modifier, and apply mean field theory using V equal to this to determine your mean field Kondo exchange. But then you can rewrite your impurity operators in such a way that one of the impurities is always unscreened in the Kondo channel. So for any, we choose these to be homogeneous, but for any V1, V2 you choose, you can always write your impurity operators such that one of the impurity operators is always unscreened. That's what we call F minus. So we redefine them. Yes. And then there's the Swins exchange, which ensures that the occupancy is 1, which screens out the singlet state.
Question. How does that project out the triplet state? If you've got 2 F electrons, they could in principle form a singlet state just as well.
You want well, because you only have one electron on each side, and it has to be magnetic moment by S equals 1. So in each one.
But 1 electron on each side, you can have a singlet state also.
Yes. Well,
Perhaps we discuss it here.
yes. Yes. Okay. So as I was saying, when you rewrite use the redefined impurity operators, you get one that is completely decoupled in the Kondo regime, so you can decouple that in the magnetic channel, and it allows that to order to by exchange. So you have one, you can split the Kondo Hamiltonian into one bit, which is the plus fermions, which you decouple in the Kondo channel, and one bit which is the minus fermions, which you decouple into the magnetic channel. So it's worth noting that this decoupling is only really valid in the strong Kondo regime. Otherwise, you would have to consider magnetic, decouple the F plus ones magnetically as well. So these are the Salois equations you get. I won't say too much about these, but you get where one for the constraint that ensures that you have single occupancy, and then one for the electron filling densities, which we keep constant. So then we consider the free energy. So we show that the free energy depends on the correlation function between S plus and the conduction electrons. That correlation function defined as such. So from the Hamiltonian, if you can show that the free energy change in the free energy depends on 2D excitation by F plus S minus. D equals 0, so we treat the anisotropy conservatively. We do an asymptotic expansion, and you can do a mean field decoupling on this. You get just the product of the expectation values, and then if you rewrite S plus using this steps, so you consider the field on the conduction electrons, which is H minus J as that, and then you assume that you're close to the ordering temperature. You can assume that the H, the magnetic field term there, which is infinitesimal, is completely dominated by the JSF term, which we diverging at that point. So then you can therefore you can rewrite the excitation value of S plus Z around TC as just the off diagonal times the field, which is just the effective field on the conduction electrons, which is just minus gamma JSF, which you then reset back into this to find that the energy is lowered if you have positive gamma. That is, if the S plus fermions and impurity fermions and reduction electrons order together. In addition to this, you can consider if V was 0, then you decouple everything magnetically, and you get entanglement between F plus and F minus, these things, for the spin one. And that would magnetically order with, now that would have an RKKY exchange with reduction electrons. But when the hybridization turns on, the F plus and C hybridize to form a heavy electron. And the F plus still has RKKY with that, but the anisotropy term feeds into the becomes the single anisotropy becomes an anisotropic exchange term between the F minus and the hybridized electrons, like we saw in the RG, which could explain the, well, we'll explain the crossings in the susceptibilities. Now, some graphs. These are the order parameters, the hybridizations and the magnetizations as a function of temperature. See, for large J equals 0, then the correlation function gamma becomes positive for TC, and these order together, and you will get a crossing in the susceptibilities, and you don't get any easy axis, easy direction phase. But for smaller J's, but still large enough that you're in the Kondo regime, the correlation function becomes positive after TC. And so you go through two phase transitions from paramagnetic into an easy direction Kondo ferromagnet, where S plus and SD aren't aligned. And then eventually gamma will go positive, and you'll get a hard direction ferromagnet. So there will be no crossing in this for that case. And you can show that gamma will always go positive at 0 temperature, actually, which I will do later. So these are the susceptibilities for two values of the anisotropy. So you can see that the effect is symmetric with the anisotropy. You get crossings both ways. And you can see that you will always get crossing for large J's. So this is the visualizing before you have a phase diagram. So in this entire phase diagram, B is non-zero. So TK, where hybridization turns on, will be way up there. So this is all in the strong Kondo region. You have a Kondo power magnet above TC. And then for some lower values of J, you will get your easy direction Kondo ferromagnets before you finally reach the hard direction Kondo ferromagnetic stage. But you will always, but the ground state is always hard direction. So for positive D, you will go from easy axis to hard axis, and negative D, you go from easy plane to hard plane. And if you have very small J, then you would move into the magnetic phase completely, and this decoupling that is not valid. You have to decouple everything magnetically, and you wouldn't get any hard direction ordering at all. This is the correlation function. So you work out the expectation value of S plus and SI on the same side, so T equals 0, given by this equation. Then you can see that it starts off negative, so at short times the correlation is antiferromagnetic, the spins are anti-aligned. But then at long times, the correlation becomes ferromagnetic. So the spins are anti-aligned, spins are aligned with each other, the S plus and conduction electrons. And you integrate this, define the temperature dependent correlation function, then you can see that this initial negative area will be swamped by this long tail, which goes like one of tau at low temperatures. You can see that at low temperatures, the correlation function will always be positive, and therefore you always get a hard axis order. And this is the numerically calculated version of this is slightly different because it's not at t equals 0. So although these are two different things, you can see that they have very similar kind of forms. So one is it starts up negative, then goes positive. So as a summary, we defined a minimal undiscrete Kondo lattice model that explains the hard axis ordering in many Kondo magnets with moment reorientation around T0, which is just above TC but less than TK. And we show that the mechanism is driven by the correlation function of the hybridized impurity and the conversion electrons. So nice little cartoon here. You have at tau at times much greater than 1 over TK, you expect the S plus fermion and the conduction electron fermion to be positively correlated, and therefore the anisotropy will enhance the antiferromagnetic exchange along the hard direction, causing the free energy to drop, and therefore that's the ground state. And then you have the standard antiferromagnetic Kondo exchange will be between the impurity and the free impurity and collection electrons. And we show that the effect is completely symmetric with respect to the anisotropy. So again, you get things both ways. Further work that we'd be interested in doing is adding more than one conduction electron channel to be more realistic to how these crystals would work. And look at the effects of moving away from small anisotropy. So in this analysis, we have assumed anisotropy to be essentially infinitesimal, which just means one of the smallest energy scales. But it would be interesting to move away from that and to look at larger anisotropies. And then more interestingly, look at crossings in the susceptibility where there is no magnetic order, such as uranium ditelluride, which is come up quite low in this conference, which has a crossing here in two susceptibilities below the Kondo temperature, which might be explained by the Kondo physics, something similar to this. Thank you for listening.
Okay, questions? Chris?
Yeah, thanks for an interesting talk. Can I do that thing where I try and say what I think you said and you tell me if I've got it wrong?
Sure.
So is the picture based, so obviously ordering along the hard direction is the hard direction. Is the picture basically that the ordered bit of the moment is setting the quantization axis for the fluctuating bit? And it's a good idea to have the fluctuating bit kind of at the top of the energy landscape, because then it's easy to flip.
So could you possibly reword that? Or?
Yeah, so I'm sort of picturing what the energy landscape looks like for spin 1. So it looks like a sand, right? There's some bit where it's going to the hard direction, then energy's high, easy direction, energy's low, and then it goes back up. But then part of that moment you're saying is being flipped by the exchange with the conduction electrons.
Yes.
So I'm trying to understand how, what my picture is for why they like it to be along the hard axis. And is it because if it's kind of starting at the highest energy configuration, there's no barrier to flipping? You sort of take it down into the saddle and bring it back up the other side.
You're asking why this goes positive, actually.
Yeah, kind of.
Yes, I mean, I was hoping someone would have some suggestions for that. I'm not entirely sure why it goes positive, to be honest. It's weird.
I think on Chris, the previous paper that you mentioned, quantities, it really is a sort of quantum order, like exactly as described. Just that the phase space for low energy quantum fluctuations of larger moments.
Because it's renormalizing the stronger coupling.
It is weird because it's.
Other questions? I have a question. Is the underscreening essential for your model? Or is that just a technical feature that you put into the model?
We did that so that we can ensure that we have strong Kondo strong Kondo screening, because all of the materials seem this effect happened way below TK. We'd expect the Kondo screening to be large, but they also have magnetic order. So with the underscreen model, you can ensure that you have if a fermion which is freely able to magnetize, so you can easily get magnetic order, but also strong Kondo coupling.
In materials such as you showed some cerium materials,
Yes.
and I know it also this phenomenon also occurs in a very famous ytterbium system, ytterbium, rhodium to silicon to, and in both those cases, I think it's very likely that the problem is not underscreened, that the number of screening channels equals the spin.
Yes, I mean,
And so that's why I'm asking the question.
yes, I mean, that's probably true, but that would make the, we were trying to determine a model that's as simple as possible and that still captures the effects. So we would like to add more conduction channels in future. Yeah, that would be more realistic.
And other questions? Let me ask one more question then. Does your treatment describe single impurity underscreened Kondo effect? One of the properties of the single impurity underscreened Kondo effect is that you get a residual ferromagnetic interaction between the electrons and the moment, which scales to zero logarithmically. Does that come out of your model?
You get a ferromagnetic example.
So one of the properties for underscreened model that is well known for single impurity is that the spin half, should we say, gets screened by the primary channel, but the second channel now develops a ferromagnetic coupling to the underscreened so you've got spin one with one channel, right? So the spin one gets screened down to spin a half, but you have a residual spin a half that then has a residual ferromagnetic coupling to the conduction C. So it doesn't screen anymore, but that ferromagnetic coupling gradually tapers off to zero at low temperatures. That's the property of the. So I guess I'm asking, did you test your approach on the single impurity underscreened?
No, I don't think it would. We didn't know, and I don't think that happened either. You do get ferromagnetic. No, I think the conduction electrons and the unscreened components are always antiferromagnetic in this model. So I don't think we see that.
Okay, thank you. Okay, let's thank you for a great talk. Our timekeeper, when shall we come back? Okay, quarter past 4. Yeah. Okay, everyone back here for Steve's talk at 4:15.